Good morning, dear students. Today we will be discussing few of the important questions of NCERT. The first question is from exercise 1.3, question number 4. The question says if fx is equal to 4x plus 3 upon 6x minus 4, where x is not equal to 2 by 3, show that f of x equal to x for all x not equal to 2 by 3. So what is the inverse of f? So we start with finding the f of x. That is the first part what is being asked. So f of x equal to f of fx, and this will be, what we do is, in place of x we write fx. So we have 4 times of fx plus 3 divided by 6 times of fx minus 4. Now we substitute what is fx. Fx is 4x plus 3 upon 6x minus 4. We can use this bracket, plus 3 upon 6 times of 4x plus 3 upon 6x minus 4 minus 4. Now if you further simplify, so this will give you 16 of x plus 4 is a 12 plus 6 3 is a 18 x 4 is a 12 with a negative sign divided by 6x minus 4, whole thing divided by 24x, 6 is a 18 minus 24x plus 16 divided by 6x minus 4. 12 and 12 gets cancelled out. Here 24x gets cancelled out. So what we have, 34x upon 34, and we know that 6x minus 4 obviously gets cancelled out. So what we get is x. So what happens over here is, we are able to now prove that f of x is equal to x. Now to find the inverse of f, we use the concept of the inverse and the definition that a function f is invertible if g of x equal to x and f of x equal to x. So we can, from the definition of the invertible function, inverse of a function, we can see that f inverse x is equal to fx, and fx is nothing else but, so we are done with this question, 6x minus 4, and we move on to the next question. Now to question number 2 for today, exercise 1.2, question number 9. F is defined as a function from n to n as fn is equal to n plus 1 by 2 if n is odd, n by 2 if n is even, for all small n belonging to the set of natural numbers. We have to check whether the function is bijective or not, and we have to give the justification also for the same. To analyze, first of all, it is important that we analyze the question. We try to understand what the question says. 2 of the sets are there, and then you have 1, 2, say 3, which takes few of the natural numbers. Similarly over here, and we try to find the image of the elements of the domain. So 1 is an odd number, so we use this one. 1 plus 1 by 2 is 2 by 2, that is 1. Similarly, 2 is an even number, we use the definition, 2 by 2 is 1. So we can see that for every element belonging to the codomain, we have 2 distinct elements over here, which will have 1 as the image. So similarly, 3 will go to 2, 4 will go to 2. So again, these 2 elements are having the image 2. So we can see, since 2 different elements are having the same image, the function cannot be a one-to-one function. So if the function is not one-to-one, it cannot be a bijective function. So the function is not a bijective. 1. Now how to write it? We just say for 1 to 1, we find the image of 1, that is 1 plus 1 by 2, that is equal to 1. Image of 2 is 2 by 2, that is 1. Since f1 is equal to f2 and 1 is not equal to 2, this simply implies that f is not 1 to 1, and this implies that f is not a bijective function. Now if someone says, the question says that you have to check whether the function is 1 to 1 or on 2, those things have to be separately dealt with, then if you sometimes want to check out whether the function is an onto function or not, we can see that all the elements of the codomain will have the pre-images. So we simply see that the function is an onto function. So now if someone says how to prove it to be an onto function, then you can say for every small n belonging to capital N, there exists two natural numbers (2n minus 1) and 2n, such that f of 2n minus 1 is equal to n and f of 2n is also n. For this one, we use this definition, and to calculate f of 2n, we say 2n by 2 is n. Therefore, the function is an onto function, and we just move on to the next question. Now, the next question is from exercise 1.3, question number 9. Consider a function f defined from positive real numbers to the set -5, infinity semi-closed interval given by fx equal to 9x square plus 6x minus 5. What we have to show is that f is invertible, with this being the inverse. So what we do is, we have fx and then we start with this function, and what we do is, we try to make x as a subject and we take fx is equal to y. What we are trying to do is, we are trying to define a function, say g of y, which is being defined from -5, infinity to the set of positive real numbers, and we will use the definition of invertible functions to show that this function is actually the inverse of fx. So this can be written as 3x whole square plus 2 into 3x into 1 minus, this is plus 1, then minus 6. So this will be 3x plus 1 whole square minus 6, y plus 6 is equal to 3x plus 1 whole square. This is plus minus root of y plus 6 is equal to 3x plus 1, or x now will be equal to minus 1 plus minus root of y plus 6 whole divided by 3. Now, do we need to take both the plus and minus? No, we ignore the negative sign because we are dealing with the positive real numbers and x belongs to R plus. So what we do is, we take x is equal to root of y plus 6 minus 1 upon 3, and we define this as g of y. Now the half of the thing is done. We have found the function g of y defined from the semi-closed interval -5, infinity to R plus. Now what we just have to show is that gauge of x is equal to x and fog of y is equal to y. So, and this is the definition what we will be using, that fx is actually equal to 3x plus 1 whole square minus 6, and g of y is root of y plus 6 minus 1 by 3. So these are the two functions what we are dealing with. Now we find GOF of x. GOF of x is g of fx. This is in place of y. What we do is we write fx. So this is fx plus 6, the whole square root thing, minus 1 upon 3. So in place of fx, we just substitute this value, 3x plus 1 whole square, minus 6 plus 6, minus 1 upon 3. Cancels out, we take out the square root, we have 3x plus 1, minus 1 upon 3, and this will give you x. So what we are able to prove is that GOF of x is equal to x, meaning GOF is an identity function on the set of positive real numbers. Now we find fog of y. So fog of y is f of gy. So in place of x we write gy. So what we have is 3 times of g of y plus 1 whole square minus 6. Now we substitute g of y, that is root of y plus 6 minus 1 upon 3 plus 1 whole square minus 6. 3 gets cancelled out. So this will be root of y plus 6 minus 1 plus 1 whole square minus 6. 1 gets cancelled out. This is y plus 6 minus 6 is equal to y. And what we see is now fog of y is equal to y, means fog is an identity function on minus 5 comma infinity. So by the definition of the invertible function, we can clearly see that f and g are inverse of each other, and therefore we can have f inverse y is equal to g of y, which is nothing else but root of y plus 6 minus 1 whole divided by 3. So now we just move on to the next question. Now this is next question is question number 4 from the miscellaneous exercise, question number 4. The question says that we have to show that the function which is being defined from set of real numbers to the open interval minus 1 comma 1 defined as x upon 1 plus mod of x is 1 1 and onto function. The first thing what we observe is that fx can be redefined as x upon 1 plus x whenever x is greater than or equal to 0, x upon 1 minus x whenever x is less than 0. And we also observe that the positive elements will have positive images and the negative elements have negative images. So while to prove this function to be one-to-one, what we do is we use the definition of the one-to-one function, and the method to prove it, we assume that let fx1 is equal to fx2, and we try to prove that x1 is actually equal to x2. This is what we will be doing. So we assume that fx1 is equal to fx2, where x1 and x2 belong to R. Now the thing is, which definition has to be used? So what we do is we take the cases. Case 1, when x1 and x2 both are positive, then fx1 will become x1 upon 1 plus x1 and fx2 will become x2 upon 1 plus x2. So if you just cross multiply, this will give you x1 plus x1 x2 is equal to x2 plus x1 x2. So x1 is equal to x2. So now when we deal with the second case, in the second case, when x1 and x2 both are negative, then in that case we can use this definition and we can have that fx1 equal to fx2 will imply that x1 upon 1 minus x1 is actually equal to x2 upon 1 minus x2. When we cross multiply, we see now this will be replaced by negative sign. X1 minus x1 x2 is actually equal to x2 minus x1 x2. X1 x2 gets cancelled out. We have x1 is equal to x2. Also, if x is positive, we have the positive image. If x is negative, we have the negative image. So we can see from all the cases if fx1 is equal to fx2, this will imply that x1 equal to x2, therefore f is 1 to 1. Now, while dealing with the onto case, we have a simpler method. Sometimes we try to find out fx equal to y and redefine the whole thing. The thing what we can do over here is we find the range of this function. So since fx is given as x upon 1 plus mod of x, what we do is we take the modulus x upon 1 plus mod of x. This is mod of x upon 1 plus mod of x. Now here we use simple concept that mod of x is always less than 1 plus mod of x, and mod of x upon 1 plus mod of x will always be less than 1. So fx will always be less than 1 and mod of fx will always be less than 1, and this implies that the value of fx will lie between minus 1 and 1. Therefore, the range of this function is the open interval minus 1 comma 1, which is equal to the codomain, and hence the function will be an onto function. So we are able to prove that the function is both 1, 1 and onto function. So that's for today. Thank you so much.